Today's lesson is on the radiation budget and the natural greenhouse effect. Take a moment to look at this diagram of what happens to all the incoming solar radiation. You'll notice that some of it is being reflected, some of it is absorbed, and some of it is re-emitted back into space. Of the incoming solar radiation, about 342 watts per square meter is the average throughout the Earth. Now, what exactly does that value mean? Well, the measure of watts is a measure of power, which is also measured in joules per second. Remember, joules is a measure of energy. So on average, we have 342 joules per second in every square meter of the Earth. This has a term, it's called insolation, which is the measure of the total incoming solar radiation, and it varies depending on different locations on the Earth based on their latitude. About 30% of this incoming solar radiation is reflected back, mainly by the clouds, but also the atmosphere and the surface. About 20% of the remaining radiation is absorbed by the atmosphere. Whatever is left over is absorbed and is used to warm the surface of the Earth, or it's re-emitted as infrared radiation. When we consider outgoing thermal radiation, if you look at this diagram, you'll see there are a number of different ways in which radiation is reflected back into space or into the upper atmosphere. We've got reflection from the clouds, we've got emission from the atmosphere, as well as radiation from the surface. And if you look at those numbers, you'll notice that a considerable amount of that solar radiation is emitted back into space. What greenhouse gases do is they reabsorb that energy and they keep it in the atmosphere. And this is what results in climate change. Most of the time when you hear the word greenhouse gases, it constitutes something negative. I want to be very clear. Greenhouse gases are a good thing, and they are essential to support life on the Earth. The temperature on the Earth without greenhouse gases will be around minus 20 degrees Celsius on average. That's going to create a very different Earth and one that will not support life. So when you talk about greenhouse gases, I want you to understand that without greenhouse gases, we will not exist. The problem is too much greenhouse gases, like too much of a good thing, can create a lot of problems as well. And that's what we're going to be discussing when we specifically look at the impact of greenhouse gases on climate change. It's important to note that there has to be a balance. So we need greenhouse gases to maintain the temperature on the Earth of around 15 degrees Celsius on average, or actually less than that. We also need to make sure that some of that thermal radiation gets radiated back out into space because we don't want too much heat, and we need that perfect balance. This is often called the Goldilocks concept as well, when we're looking for planets that are not too hot and not too cold, but just right. The radiation budget is where all of this comes together. So the net radiation budget is basically the difference between all the incoming radiation and the outgoing radiation. And what we need in order to maintain the average temperature on the Earth is a net radiation budget of 0. And in order to do that, we cannot contribute to changing the amount of incoming or outgoing radiation. We can't really change the amount of radiation coming to the Earth from the sun, but we can definitely influence the amount of outgoing radiation. And this is where the whole discussion of climate change comes into being. Now, you also need to know that about 1% of all the incoming solar radiation is photosynthesized into chemical energy. So as much as we need that incoming solar radiation, it is only a small amount of that that is actually utilized to maintain the food that we need for life on Earth. It's important for you to understand what quantities we're dealing with here. So the less than 1% of the energy that has been stored on the Earth in the form of fossil fuels is what we are trying to access. When we access that less than 1% of energy stored as fossil fuels, we're releasing its thermal energy into the atmosphere. And as a result, we're also producing greenhouse gases. And it is that extremely small amount of less than 1% that is putting our entire radiation budget out of balance. Now, you might look at that and think, well, it's less than 1%. How could that have an effect? Well, that's why we had to look at the net radiation budget, because anything putting that out of balance is going to change the average temperature on the Earth. So take a look at all these different greenhouse gases. Now, most of these greenhouse gases you have probably heard of before, and you're also likely aware of where they're coming from. So for example, methane from the digestive system of cows, or carbon dioxide from the burning of fossil fuels. Now, if you look at these greenhouse gases and I ask you to pick the greenhouse gas that has the greatest impact on increasing the temperature of the Earth, you may choose things like methane or carbon dioxide. But the most powerful greenhouse gas of this list that you see in front of you is actually water vapor. Now, if you're thinking, well, we always talk about carbon dioxide and no one really thinks of water vapor as a negative thing, then that's true, because water and all these greenhouse gases, remember, are an important part of keeping the Earth's temperature at an average where humans can survive. So when we think of things like water vapor, we're not thinking of it as a negative greenhouse gas, and it isn't. But here's the problem, and this is what results in what's called a point of no return, which I'd like you to write down on a separate sheet of paper. So the point of no return is when we start producing all these greenhouse gases by burning our fossil fuels or having massive amounts of cows and livestock and so on, we're going to release things like methane and carbon dioxide into the atmosphere. We have control over these gases. They're going to trap that energy, that solar energy, on the surface or in the atmosphere, and therefore increase the average temperature on the Earth. The problem is the Earth is mostly water, and this is why I picked the slides with water in the background to remind you of that. The Earth is mostly water, so as the temperature of the Earth increases, the amount of water vapor increases, because some of that water is going to naturally evaporate, and that's going to add water vapor to the atmosphere. Water vapor is the strongest greenhouse gas. So it's going to do the best job at trapping more heat on the surface of the Earth or in the atmosphere, which is going to cause more water vapor to be produced as more oceans evaporate some of that water, or lakes, and therefore more water vapor is going to get into the atmosphere, which is going to in turn increase the temperature of the Earth. And this cycle is called the point of no return, because we do not have control over water vapor. We do have control over carbon dioxide and all the other greenhouse gases that we produce as a result of things like burning fossil fuels or having livestock. We cannot control water vapor because we're already on an Earth that is filled with water. So this is called the point of no return, and this is a point that we want to avoid, because we don't want to get to the point where water vapor takes over, because then there's nothing we can do. We can get rid of all the cars and all the livestock and all of the pollution that we're producing. We cannot get rid of the water. So as a result of that, we want to avoid getting to that point. And this is the most important thing you need to understand about greenhouse gases. So here's an important statistic for you to write down. For most of human history, the amount of carbon dioxide on average on the Earth has been around 280 parts per million by volume, right? So there are 280 parts of carbon dioxide per 1 million parts of anything else in the atmosphere. In May 2020, this number has increased to 416 parts per million. And that is a considerable increase. And that is what we want to avoid and we want to reduce. To end off, I'm going to show you this example over the last 50 years, from about 1960 to about 2010, of how the atmospheric carbon dioxide levels have changed in Mauna Loa in Hawaii. Now, the thing that I want you to note from this is not just that they've increased, because that's obvious by looking at the graph, but also how rapidly it has increased, from a number that was between 310 and 320 parts per million to a number that's around 380 parts per million. That is a significant increase, and this is something that's often left out of the discussions with climate change. Climate change scientists are not ones who are just talking about the fact that the Earth's temperature is increasing on average. It is also important to understand that the main concern, beyond the fact that the temperature is increasing, is the rate at which it's increasing. The Earth's temperature has been increasing throughout history of humankind being on Earth, and even before that. What's different is that this increase is very rapid. And it's so rapid that this is one of the problems associated with climate change. Can the Earth really be able to tolerate not only an increase that is unprecedented, but also an increase that is so rapid?